started here on the lecture. Thank you guys. We're trying to figure things out. Please join the live Q&A if you are remote. I've asked you to download the handout PDFs, which was a link that certainly worked last time I tested it, but doesn't work now. I apologize. I will fix that right after lecture. Well, I have to do a hospital visit, but then I'll fix it after lecture. I apologize for that. I don't know why it got wiped out. Similarly, I don't know, the Echo 360 Live should be working now. If not, if you could write something in the live Q&A, that'd be great. But since you're not hearing me, I guess we will not know until later. Okay, so actually, if it does work, if you could say something on the live Q&A, if you can hear me, if things are good, let us know. All right. Today we got a handout for those of you physically here. Thank you for coming on this beautiful day. And there's a handout, and please sign your name so you get credit for being here. There's automatic registration of people that are watching, so they don't have to do anything special. But for you guys, please write your name. I very much appreciate you coming in person. Not just because I think it's better for you, but it certainly helps me. That way I can tell if I'm going too fast or if you guys are comatose or whatever happens. So I appreciate it. Let's see here. Yes, so I will fix the online handout link. In fact, I will write that down for myself so I do not forget. If you notice any links like that broken in the future, please let me know. There should, there's a bunch of links there. If they're broken, that's not intentional. Maybe refresh your browser, but if you've done that and it still doesn't work. I've been told the sound examples links works, but I'm actually not hosting that privately because I couldn't, when I tried to upload the sound examples, the system gagged. So I used a private server, just one that I pay for that actually does that. You're not required to download those sound examples. It's like half a gig of stuff because some of those things are on YouTube and elsewhere, but for me, for reliable work here, if the network is down or something, I need to have it all. And, yeah. So, but you're welcome to download them. Should be no problem. As I say, those are just there so that you can listen higher quality if your current quality is low. Hey, look at that. Echo 360 is working. You are too cool. Dude, I can't remember faces or people, so anything really cool you do like that, I can't actually give you an A+ for it because I can't help. But anyway, thank you very much. I appreciate it. Yes, mostly for those of you here, I do have face blindness. I can't recognize people. I have terrible memory problems, and I can't multitask. So, typical old doddering guy. Okay, so let's see here. Next lecture, we're going to do an in-class quiz. For those of you listening remotely, I will email it to you. Please email it back, certainly before the lecture is over. For those of you who come here, I'll have a paper version so you don't have to bring your computer if you don't want to. The quiz, I can tell you ostensibly, is only there so that you actually read the handout. And I will ask you questions. I do want you to read the handout. It does help now that during COVID, we have a lab monitor there all the time. So in the past, it's been a real problem that in the first lab, people rewire the whole place, and then it's very hard to figure out what happened. But now there's a lab monitor there, so hopefully things will run smoother anyway. But I will have a quiz. I also just need to know how the course is running and such. So the quiz may be more or less challenging this semester, probably less, but I still want you to do it. Also, it will give you a chance to email quiz answers to the proper email address, the same one you use for handing in homework. Okay. This is about in lab, the Mackie mixer. About a quarter of you have done lab already, but many of you haven't. You will see this mixer in lab. This was in the first handout, which I'm hoping you started looking at anyway. this is just a reminder for the sanity of others. On the back panel and on the top part here with all the connections, please don't change patching. Please don't change switches in the back. In particular, there's this phantom power switch. I'm going to mention this now. If, for whatever reason, in the future you would like to bring in your own thing, especially something you built or your electric guitar or something, and feed it in there, feed it into one of these inputs, make absolutely sure that phantom power is off. Phantom power is something for microphones. It was a horrible hack that some engineer thought of some time ago where the device, namely this thing, you're plugging in a microphone, so your signal is going to this mixer, but the mixer provides power for your microphone. So it was an easy hack. That way you don't run out of batteries all the time and that sort of thing. Unfortunately, what if it's not a microphone? That's feeding it. Well, you can easily burn up circuit, right, by putting high voltage DC out to it. So just beware of that. It's one of these evil things that have wrecked a lot of student equipment in the past. So that's the phantom power. Please don't mess with that or anything else. If you're going to plug something in, check that it's good. The phantom power actually only affects these microphone inputs, but still, if you connect up your own stuff, you can use unused inputs on it. The ones that say no or bad, guess what? Don't use those. They probably won't work. But the other ones work. The other thing I really want you to know is what these mute buttons are for. So this is a mixer that's made by a very professional mixer company that makes good mixers. And this is a really low-end one of theirs. But the nice thing about being a low-end of a fancy company is that you have features that are useful in practical situations that your Radio Shack mixer wouldn't have. So it's not just audio quality, it's lots of other things too. I guess Radio Shack is no longer a thing. Everybody know what Radio Shack is? Okay, good. At least that still exists. I'm getting old. So this mute button, it says mute, but then underneath it says Alt 3-4, and that's actually a routing button. Because the way we use it, because I didn't want to buy yet more equipment, in a normal situation, in a live situation, it's really useful for the guy at the mixing console or the woman at the mixing console to check what all is muted right now and to listen to all the muted signals. So that's Alt 3-4 output of the mixer. Well, we use both. So if you leave it unmuted, it goes, basically the mute button determines, does it go to the input to the Egan matrix, like the digital audio input to the Egan matrix, or does it go to the speaker? And those are totally different things, right? So the mute button is not for muting your sound. If you want to mute something, turn down the volume knob. Each or the gain knob, as it's called here. All right? Now, if you got time and you are so inclined, please check out the drawing of the mixer. You're not going to be quizzed on it or anything, but it's a cool drawing, and it's kind of fun to actually fun if you have the time and if you're enough of a nerd. But try to track it, try to figure out what it's doing, because that mixer is actually quite a good circuit. It also, the way they do their drawings is very typical of sort of shorthand drawings done for equipment where you really need to know how they work. It's nice that they're labeled, well, like the mute button is labeled this way, but what does it really do? You can look at that drawing and figure it out. So it doesn't show you enough so you could recreate the circuit. And, for each one of these columns, it just has one of n, but that's fine. It's enough so you can figure out really what's going on. Yeah, and the mute button, and this will be on the quiz, so be sure you understand that part well enough, because it's one of the biggest problems we got. Yeah, the mute button, we're just using it for routing, and I was just trying to explain why would a mute button route it one way or the other. Well, we're misusing this device because we can. Because it's an active mixer, and it actually has multiple output channels, because even though it doesn't look like it, or multiple output paths. All right. So there's all these other buttons and knobs here, like pan knobs and stuff. I don't know. Just resist the temptation to twist knobs endlessly. This is showing the default position of them, so you're welcome to put them back in the default position. But other than that, please be nice to the next person. Okay, so this first part of the course is an incomplete history of electronic music. There are many histories of electronic music. There's lots and lots of things going on. If you are interested, I still have one of these left. I used to have 5. I lend these out, but these are so cheap that when they don't come back, although this is my last one, maybe do try to return it. Since I can't remember people's names or who they are, I often lend out things that don't come back. But in any case, this is a nice book. It's not even color pictures. You know, it's not that old. It's just that it was done on a budget. So if you are interested, it just has a summary of lots and lots of synthesizers and stuff in it. Kind of interesting read. Mark Vailden, nice job. So you can also look online, but, you know, it's always a shorter list of things. This guy actually spent several years, you know, figuring out how to do this. I don't know. I like the book. So it's something to look at if you are interested in such things. I'm going to give you a history of things that I thought were cool. It's not, you know, not nearly a complete history. In electrical engineering, it's very rare to have any history of anything. You know, if something was invented yesterday, you know, nobody knows or cares. Like most electrical engineers don't know that, for instance, fax is older than telephone, and that, you know, and how these things developed and stuff. I have no idea. But it turns out that it's actually, you know, kind of cool. In music, people reference this stuff. So it actually is really useful to have seen it. The other thing I'm going to do is, in this history part of things, there's these technical terms. And if I bowl through this and don't tell you what all those technical terms means, just raise your hand here or write something on write something on the real-time QA. If anybody in class is watching that, or you happen to notice, let me know. I have to get used to looking over here all the time. So what else can I say here? So we do this historical things. It's to introduce terms and ideas to you, too. So it sort of kills multiple birds with one stone, if you like that terminology. Okay, so electrical engineering, music technology in 1900. We're going to start in 1900. What was going on? Well, you know, it was the birth of electrical engineering. Most people don't know who started electrical engineering as a field, but of course it's Tesla. Everybody knows that now because of the car company. And maybe you saw the Current Wars movie. I used to talk about this for a while because people had no idea, even if they were from Chicago, what the Columbian Exposition was. Didn't know that, you know, just amazing things they built there. And then talk about throwaway society. Tore down most of it, right? They left the Museum of Science and Industry and the Art Museum, but there were many other buildings. There were all sorts of cool things there, and for whatever reason, it was all torn down afterwards. It was never meant to be permanent, but those buildings have survived. At that point was the first time that Tesla got a chance to show how AC power really did. So anyway, I highly suggest the Current Wars movie. I think it's actually one of the best. You know, it's entertaining, but I think historically it's as good as anything else you're going to read. Just because either people ignore Tesla, like in our towns here, you know, every town has a Edison school, but, you know, nobody has a Tesla school. So either they totally ignore Tesla or they totally vilify Edison. Tesla was certainly more mathematical and invented or really, nobody invents anything from scratch themselves, but he really got AC power going, and that's huge. We still use the same sort of three-phase power that he came up with. So that's just huge. But Edison had many other inventions. Maybe got too much credit over time, and, you know, it's unfortunate that we still have the electric chair, you know, which started as an advertising campaign against AC power. You know, there's a lot of bad history there. But Edison himself, as was portrayed in the movie, knew that was an idiotic way to kill people, and he shouldn't have let it happen, but it certainly got out of hand, and he would have been chagrined to know that we still use that now. But one of the greatest inventions that Edison did was the phonograph. It's huge. Now, he was always embarrassed about it. Of all the things he invented, he thought it was kind of dumb, and people were too centered on it, but it's enormously important in the music world. Lots of things happen when you have recordings. One of the biggest is, it used to be everybody played music themselves. And, it was the beginning of like what we have now, where it's rare for people to actually be able to play an instrument themselves. It's rare for people to go and listen to music in a coffee shop. Live music, I mean. It's, all these things that, even when I was a student, Zorba still had a piano, and there was still there would always be somebody sitting there with a hat out once they got enough money to go buy the sandwich, the next person would sit down. And, all that's gone. We're continuing down that path, but if you want to read something sort of interesting, there's a John Philip Sousa, who was professor here for a while and led the bands here and invented the sousaphone, among other things. He wrote a diatribe about how horrible the phonograph is, and there's a lot of truth in it. You read it now and you kind of laugh until you figure out, wow, a lot of this has sort of come true. So there's that. So that's sort of on the negative side. On the positive side, boy, it raised the bar. Once people heard recordings of people that actually played skillfully, then, you could no longer get away with being a really crummy player. And so there are cool things about it. But that's sort of the background of where we're starting this history. Are there any questions about that? Okay, there is is there a schedule somewhere by dates which we should require readings? There's not an overall separate schedule. So what we have is in the handout on every Tuesday, there is, at the end of the handout, is the lab assignment and the reading assignment. There's not a separate schedule for that. The reason I do it that way is because, well, historically, people come to class and I give them one handout and they prefer that over 15 different sheets. So in any case, that's what I'm doing. So you got to read the handouts anyway. And if you look at the first handout, you'll see that the lab was in there and the lecture assignment was in there. It'll be more explicit in the future. But at the very end of the handout, you'll always see it. Okay, my mic is peaking too much. Okay, main volume. Let's see if I can do something here. Doc cam. Yeah, in the room here it sounds okay, but settings, audio, table mics, wireless. Okay. What is my microphone? A main? A table mic? Or no, it's not the main. It's not a table mic, so wireless must be this thing, right? Zoom. Okay, I think it's quieter. Yeah, that worked. Okay, so let me know, Armand. Do let me know if this gets better now, or if it's too quiet. I might be fishtailing here. So let me know. Okay, so next we've got additive synthesis. Additive synthesis, what is that? So this first term here is additive sine wave synthesis. That's basically this method of making a complex sound, of building up a sound out of individual sine wave components. All of you know from your signal processing classes that you can add up, that you can take any signal, break it down into sine wave components, right? That's what the Fourier transform does for you. Well, you can go the other way. You can start with sine wave components, add them up. Now, unlike the Fourier transform, additive synthesis generally doesn't have every possible sine wave component in it. You know that a Fourier transform is invertible, or in another sense, you can make any conceivable sound by adding up sine waves. But you have to have a lot of sine waves. You have to have them with the proper phase and amplitude. You know, there's a lot that goes into it. When we do additive sine wave synthesis, you don't really have all the sine waves. What we have is certain sine wave components. And this is true of, like, once you have a stable standing wave pattern. Uh-oh. Now it says nobody can hear anything. Should I turn it up again? I don't know. Here, in between value. Hopefully this will peak less. Okay, so an additive sine wave synthesis, we use fewer sine wave components, and normally it's just harmonic components. That's the most common, not always. Sometimes we use more than that, but usually it's the harmonic components. So if you think of a standing wave pattern, right, you've got a fundamental frequency and only integer multiples of that fundamental frequency. So those integer multiples are the ones that usually in additive sine wave synthesis are used, although more modern additive sine wave synthesis does other ones. In this case here, we have additive sine wave synthesis. Now we have these words. There's overtone, which you know from your music background, or partial, which is electronic music word for sine wave component. It might be a multiple of fundamental frequency, it might not. So partial is specifically meant to avoid that. Because like, say for instance, you do an additive sine wave synthesis of a cymbal. Well, for a cymbal crash, you definitely need non-harmonic stuff. You need a lot of sine waves to make that sound good. Okay, then there's the word track. That's also a sine wave component from the speech community. And then there's harmonic, which is used by engineers, usually for only integer times the fundamental frequency. For musicians, use it more generally, just for any overtone, call it harmonic. So all those things, overtone, partial, track, and harmonic, are all just a sine wave component of a sound. Okay, so those are all sort of synonyms from different places. Sometimes they mean something very specific to somebody, but they're just synonyms from different places. Then there's frequency ratio. So for the Telharmonium, the frequency ratios are 1 to 2 to 3 to 4 to 5 to 8 to 10 to 12 to 16. What that means is 1 to 1, or the 1 here indicates that's the fundamental. 2 to 1, or the ratio 2, or 2 to 1 means an octave up. 3 to 1 means an octave and fifth up. 4 to 1 means 2 octave ups, and so forth. Right? So it's just the frequency of the sine wave component divided by the frequency of the fundamental. And these are the ones that the Telharmonium had. So fundamental is the frequency, well, for a harmonic sound, it's the frequency you hear. It's what you identify as a pitch, like an A440 or something. All right, so those words. So at the time that the Thaddeus Cahill made the Telharmonium, he had 30 boxcars worth of generators that he brought to New York City, and it was going to be something, in an early phone system, you paid a lot of money for a phone, and there were the 18 other people that had a phone, or, and that number grew, maybe hundreds after a while. But you had this phone system, and there weren't that many people to call. You paid a lot of money for it. So the idea was, when you aren't talking on the phone, you can listen to music. So the Telharmonium was for the first phone system to play music into it. Now, they didn't have, at that time, there wasn't the technology to do amplifiers. So they made big generators that would generate all these different frequencies, and there were drawbars on the keyboard where you could control the amplitude of the various harmonics. So the output of each generator went directly into every phone. That's a lot of power. So one of the big problems with the thing was every time a new note was played, it's a big lever that you press, almost like the alt-geld chimes, but every time you press the lever, there's a huge amount of arcing and stuff going on as all this power went to power the whole phone system. So it was a bit raucous. But there is this question: if you got drawbars, if you can control the amplitudes of all the harmonics, then is it possible to play any timbre? Is it possible to make any sound imaginable? And you got to be careful now. Like everything, when you're an engineer, or especially working in music, you can read all sorts of results from other engineers that are true and then misapply them. So in 1862, Mr. Helmholtz showed that all sustained sounds, and I circled sustained because you got to know what that word means. But all sustained sounds can be characterized in terms of harmonic frequency components. So every sustained sound only matters how loud are the sine wave components, how loud are harmonic partials. So the only frequencies present are multiples of the fundamental, and it doesn't matter what the phase is. The only thing that matters is how loud are they. Well, here you got a machine that at least has, so it's missing the 7 times the frequency, 9 times the frequency, but it's got most of them, and it's got drawbars to say how loud it is. Now the question is, well, can you make any conceivable sound with this instrument? It's like an early synthesizer, right? I mean, even earlier is pipe organs, but we won't go into those. It's an early synthesizer. And can you make any conceivable sound? Of course, the answer is no. What was that about? Okay. Here, I'm going to ask here, is the level still peaking like crazy? Question mark. You can't press return to send it. Okay, where is it? Received. Give me a button. There it says post. See, even an old guy can figure this out. Okay, so that is, there is this thing about repeated waveform, and the thing is that you don't ever listen to sustained sounds. Any sound you listen to changes over time. It's not totally true for synthesizers nowadays, right? If you listen to a sawtooth wave, hey, you can really not change it. And actually, it really doesn't matter what the phase of the harmonics are in a sawtooth. Only their amplitudes matter. It will sound exactly the same. So you have infinite number of waveforms that sound identical to a sawtooth. And that is true. But the fact is that most sounds you listen to aren't generated by a machine that fits this exactly repeating thing. Even something acoustic that's like once you have a standing wave pattern, nothing is perfect in the acoustic world, right? So it's always an approximation to this ideal, and only a synthesizer would be able to produce you exactly repeating waveforms. So it is true that the thing could have made, for instance, a pretty passable sawtooth because you just set the drawbars right and you can get that sound. Okay. Questions about that? I'll set it down just a little bit more here just to clip a little less. Okay. Okay, so what else we got here? Okay, so that's it for the Telharmonium. Okay, what do I mean by drawbars? So on an organ, a pipe organ or electronic organ, a drawbar is basically something you can pull out or push in to get different amplitude. So it's kind of like a knob on a synthesizer, or maybe a slider on a synthesizer is a closer analogy. But yeah, so it's just a way to set an amplitude value in this case. Okay, so heterodyne technique, Leon Theremin. He is a Russian. Amazing dude. Now, unlike the Current Wars movie, how many people saw the Current Wars movie here? Oh, bummer, man. Oh, okay. Well, anyway, I used to talk a lot about what went on there because it matters, and you should know as an electrician, and it's entertaining. You should watch that thing. I know it's historical. I was afraid to watch it too, but my wife made me watch it, and it was worth it. It was good. There is no such movie about Theremin yet. Theremin also, well, he built what we call the Theremin. He didn't call it that, but there's this excellent book by Albert Glinsky. Now, this book is historical. So it's a much harder read. It's not a novel. It's not like that movie, which is easy to sit down and watch. This is this doesn't feature Cumberbatch or any other great actors. It's really a historical thing, so it's a harder read. But anyway, this guy was amazing. So I just want to say this book actually is also written by a local historian, but he is very famous in music, but is also responsible for much of the Cold War. And much of our fear that Russians have insane technology that we can't fathom. Yes, so he made one thing I can mention here is a passive resonator. When our spy plane, the U-2, which also, of course, the band is named for, but when our spy plane was flying over Russia, we claimed that, oh, no, that's not a spy plane, and, why did you shoot it down, and all those poor passengers, or whatever we made up. And Khrushchev at the time was smart enough to keep the pilot alive. So, yeah, he had absolute proof it was a spy plane the U.S. was flying, and he presented this at the UN, a very famous speech where he took off his shoe and was pounding on the podium for emphasis. Very impressive. And of course, bald-faced lies from our side. So CES didn't really know what to do. So instead, they instead of actually denying it or anything, they went up and showed this passive resonator, which they'd finally discovered after many, many years in the embassy at in Moscow. It turns out in one of the most private meeting rooms, even if you whispered in there, the Russians could listen to every conversation in there. And they'd given this beautiful big eagle thing to hang, as a gift and a show of friendship to the Americans at the embassy there. The Americans checked it very carefully for any electronics, for any antennas, for anything, that could be wrong with it. Couldn't find anything at all. It seemed on the up and up was a nice thing, so they hung it up in this in their coolest room. And it was much later that somebody was trying to tune the AM radio and heard this conversation. They worked at the embassy and realized, oh, wait, this shouldn't be happening. So what it is, he had a passive resonator, which is a device that doesn't look like much. It looks like a fat tube on one, or a fat bulb on one side, and then narrows down to a smaller bulb on the other. He'd figured out that a device that you could shine microwaves at, and then those would be modulated by the audio in the room passively and resonate, and then you could pick that up with a radio at a distance. And, it is true that microwaves are harmful, but it actually was totally exaggerated later because Americans were mad about it. But even at the time that Americans showed this device at the UN, they had no idea how it worked. It was just terrifying. They had all this magical stuff. The U.S. had soldiers, as did other countries, had soldiers that tried to get into Siberia or other parts of the Soviet Union in the middle of nowhere. And they would just end up dead. And they know that nobody would, there were no enemy soldiers stationed there, so they couldn't figure out what happened. Well, he'd also invented the motion sensor, and they hooked up rifles and such with them, so people would be shot by automatically, and all these horrible things. So which was interesting because Theremin himself had gone to a death camp but survived it against all odds and still went back and worked for the KGB. Anyway, very weird dude. Very hard to understand, but he was a big hero here when he was in the U.S. He was very good at investing. He obviously hated capitalists, but was very good at it and sent all his money to his communist friends. He was married to multiple people at the same time that didn't know each other. Everything nefarious you can think of, he done it. Very weird dude. But he also built this very cool musical instrument. In fact, this musical instrument, before the war started, and they faked his abduction, everybody figured he was dead. Nobody even knew he was alive anymore. He had gone to visit all sorts of factories and really sensitive things all over the world because he is this great inventor that everybody was amazed by. So they showed him all sorts of things that were then very useful information for his communist overlords. But he invented the Theremin. In 1920, he was in New York City when he did this. So there are technical terms here. Heterodyne, beat frequencies, hand positions, and, the passive resonator I'm done talking about. It's not really a musical instrument. It's just pretty amazing. And the thing that really escalated war technology, really got it so that we worked on all our high-tech stuff. So what does heterodyne mean? Well, the heterodyne technique is actually something you've seen before. If you think about a Fourier transform, the way you actually do it, or AM radio, or a lot of different things, you multiply one set of sine waves by other sine waves. Right? If you actually look what a Fourier transform does, it's just multiplying by sine waves. To shift, and then you get difference frequencies, and you can integrate them. You can do whatever whatever you're doing in your technique. So in heterodyne basically just means, hey, you're shifting the frequency of something by multiplying it of a sine wave by multiplying it by another sine wave. Or it might be more complicated than the sine wave. It might be a signal, but most basically it just means you're listening to difference frequencies. Okay, so at the time in 1920, it was not possible to build a audio, or at least nobody in the U.S. knew how to build a audio rate oscillator that was in tune. So Theremin did this brilliant cheat. he used beat frequencies or difference frequencies and the human in the feedback loop. So here's Clara Rockmore. I'll play her playing in just a second. There's two antennas here, the pitch antenna, which is one we're mostly concentrating on, and then there's a volume antenna. The volume antenna is a little backwards than what you think. As you get farther away from the volume antenna, it gets louder. But, yeah, it's basically by position you're controlling volume. The pitch antenna, you don't even touch this instrument, right? I mean, and, this is 1920s. Nowadays, still, when people see theremins, they think, wow, that's so new and modern. Yeah, it's 100 years old, new and modern. But the pitch antenna then controls pitch. The notes is not updating on echo. How is that possible? Okay, you need to refresh your screen if the notes aren't updating. I'm sorry. I'm not a fan of COVID, but I guess none of you are either. Okay, so we do what we have to. Okay, so yes, so we have this pitch antenna, and I made a little simplified graph here, which really is useful to screen capture or copy or whatever it is you want to do. The circuit here is going to be too hard for you to understand unless you are familiar with tubes. Every year I have students that know their tube circuits, but better than I do. But what is going on here? Well, I want you fundamentally to understand how this, in this case, this heterodyning technique works. There's a fixed oscillator, which is oscillating 170 kilohertz. That's way above your hearing and even your favorite cat's hearing. Okay, that's a high frequency thing. But then there's a variable oscillator, which is really close to 170 kilohertz. But it has this antenna in its circuit, so it has a variable, this pitch antenna. So, and as you move your hands closer and farther from the antenna, the capacitance changes. So that controls the pitch. So you're basically taking this oscillator and changing capacitance in the circuit, so the pitch changes a little bit. So maybe you change it down to 169 kilohertz. Well, then what you're hearing here on the output is the one. I mean, you certainly won't hear 170 plus 169 kilohertz. I mean, that frequency exists in some sense, but you don't care about that. You hear the difference frequency, 170 minus 169 kilohertz. You hear the difference frequency between this fixed oscillator and this one that's near 170 kilohertz, but your hands are messing with the frequency. And so you're hearing the difference frequency. This isn't strictly speaking a multiply in the super accurate multiply sense, but close enough for our discussion. So then we have a power amplifier, which didn't exist for Telharmonium's time, but exists in vacuum tubes now, going out to a speaker. And that power amplifier is controlled by the variable amplitude, again, with a circuit that's controlled by capacitance. But, yeah. So, so what you're hearing then is the difference frequency here, and that's called a heterodyne technique. Very important, because there's no way you could have made a good audio oscillator at the time. And you may have heard things like that just from trying to tune your AM radio and stuff. You know, there's situations where things like that happen, if you have ever tuned an AM radio, I guess. But that's something to know. So this is a really cool instrument. You don't play it by touching it. So that's pretty darn bizarre and looks really cool to the audience. Now, is that a good design? Well, it depends. First of all, as you will learn, in acoustic instruments as well as electronic instruments, the limitations of the instruments are often what make it beautiful too. So, you know, this idea that one size fits all is a mistaken idea. So I can play you an example now of just beautiful playing. If you look on your hand out there, there's that hand position system. What is that? Well, there's different ones, but the idea is that if you really are just trying to precisely move your hands, it's just too hard. So what you do instead is you find the right pitch. It might depend on humidity some, it might depend on anything else, so you got to have a good ear. But you find the right pitch, and then as you do scales, you move your fingers into different positions, like there's 4 positions shown here, which change the capacitance just enough to go to the next note. And so in your mind, you're sort of making, it's unnecessary in a sense. You could just have moved your hand, but it's a way to play more precisely and have references for yourself. So then the way you do vibrato is you move your hand. But the way you play different pitches, or the accepted way, as I say, when I heard theremin for many years, all it was is ghost notes, but this is way beyond that. Any ECE courses I teach about vacuum tubes? Anybody here know? Actually, I don't know. I was sort of self-taught because my predecessor in this course actually came up with this circuit and other circuits. I had no clue what they were, and he just sort of assumed we knew that. So I do not know. Email me if you want. I do know somebody who really works with vacuum tubes quite a bit. There's a lot of interest in them, and maybe learning from other smart people that don't happen to be professors but are super smart will be useful. So go ahead and email me that, and I will put you in touch. All right. So I was going to play you a sound example here. This is Clara Rockmore playing on the theremin, and I hope this comes out in reasonable quality for people out there. If not, there is that link of half a gigabyte of stuff, but hey, you can delete it after you're done with it. It has a sound example. This is Clara Rockmore playing Rachmaninoff's Song Without Words. Quite beautiful. There's piano accompaniment. So you hear something that sounds, well, you hear the theremin and you hear piano accompaniment. And the two against each other are gorgeous. It's one interesting thing about the theremin, how gorgeous it is with acoustic instruments. Very often, electric and electronic stuff with acoustic doesn't work very well. But this is just amazing, I think. Rachmaninoff's Song Without Words. So Clara Rockmore was quite a good violinist, and then met theremin and learned to play theremin. So she had experience with vibrato and stuff, but this vibrato is much wider than you would have on a violin, and it's a very typical sort of theremin sound, but quite beautiful, and still one of the most beautiful and expressive electronic instruments I think there is out there. Any questions about that? No, the question is, was that singing? No, that's not singing. That was her playing theremin and just theremin. She's just very good at it. And yeah, you can do sort of voice-like things with it. It's if you listen on further in that recording, like when it gets in the lower ranges, it clearly sounds unvoice-like. But yeah, it's quite beautiful. There is one of the most famous uses of the theremin was for the original Star Trek theme song, which is has wild vibrato and high pitches. And anyway, turns out that thereminist hadn't practiced enough and couldn't play in tune on the day. And there was a singer there that said she could do that, and she imitated that theremin so well that for decades I thought it was a real theremin. So anyway, there are people that can imitate the theremin, and theremins that can imitate people. It's all very cool. All right, so the next thing here is coded performance. Now, I'm going to play you an example here, which is from, I don't know how to pronounce this name, Nankaro. I won't even try the first name. Colon, or I don't know. Anyway, he is. People are from all over the world. I can't say many of these names, but he is from Mexico. And this recording I'm going to do is from a 1920s piano, but this piece was done in 1947. It's called Rhythmic Study Number 1. And so what about this coded performance? What does that terminology even mean? Well, it means that instead of writing music and then somebody's playing it live, you prepare it ahead of time. And nowadays, that's sort of a no-brainer, right? There's lots and lots of digital audio workstations and notation programs and all sorts of things that you can use and are setups to do this, or you can use music and languages. We'll talk about them later if you're not familiar with those. But there's lots of ways that you can make a list of notes and say how long they are and how loud they are and all those things. But it's a really big deal, this difference between what can a human play and what can a machine play. So in this case, he was really interested in rhythms that weren't precisely playable by humans. And so he would compute timing and dynamics according to various formulas and such that he was using, and then hand cut the paper for piano, piano roll paper, which is a sense kind of programming, very slow, but kind of programming. He would cut those. So instead of having a piano roll made by having a famous performer sit down on a piano that would cut the roll, in this case, it was just the roll was cut by hand, very carefully measured and cut by hand. Insane amount of work. In this example here that I'll play you, this is what was I going to say about it? It's called Rhythmic Study Number 1, performed publicly for the first time in Mexico City in 1947. You can listen to all sorts of things here. In this case, the various voices have tempo ratios of 1 to 3 to 5 to 8 to 14. So, used against 3 against 1, triplets or 5 against 1 or whatever. But anyway, he has all these things going at the same time. So you can listen for the different tempos going on at the same time. The thing that's easiest for me to hear the first time is just that the second half is a retrograde inversion of the first half. When you listen to this, it's different than listening to that previous thing. I don't mean this as an insult to Nankaro at all, but to me, this kind of stuff is much more like a crossword puzzle where you're trying to, than a novel. The previous thing is more like a novel. It transfers all these emotions and such. This, to me, is more of an intellectual exercise. But like I say, every semester I have some students that really love this. And so this is a very early coded performance. So anyway, it took me many listens to hear it. I'm just not trained in this sort of thing. Where I've had other students that could tell me all sorts of things about it. Okay, so in the next thing I'm going to do here, this is from France now. This is Maurice Martenot with Ondes Martenot. The Ondes Martenot is a device that he worked on, unlike Theremin, who is this? Seems like it's really overexposed. Oh no, this one's better. That displays just no good. Okay, unlike Theremin, Martenot spent his life on music and kept improving the Martenot. So what I'm talking to you about today is really the early, the first ideas and such, because the later versions of it, and like what actually Radiohead plays now and stuff, has many ideas integrated from others, even things that came after this initial 1928 thing. So for new terms here, what is tremolo? Well, in violin playing, it means fast repeated notes. But anyway, we're not talking violin here. We're talking about electronic music. So in tremolo, in electronic music means a repeated amplitude variation, getting louder and quieter, quickly in amplitude. Where vibrato on a violin, again, you're rolling your finger, and the amplitude changes a little bit. The pitch certainly changes. The timbre changes. Lots of things change. Any acoustic instrument, or like for these are more complicated things. But electronic music specifically, vibrato means a frequency variation. So if you're doing the bend wheel on a synthesizer, that's what vibrato is. And tremolo refers to, in electronic music, refers to amplitude variations. In almost all acoustic instruments, the two are always combined, the amplitude variation and the frequency variation. But in electronic music, they're almost always totally separate, unrelated issues. Okay, so then there's the idea of a controller. On the left side of any modern keyboard, MIDI keyboard, there are controllers, right? There's bend wheels, there's sliders, there's buttons, all these things. He did that back in 1920s, and it was a good idea, so we stuck with it. So on the left hand here, it's a little hard to see in this picture, at least that projection is not very good, but in this picture here, there's a little box that slides out, and there are various things you can touch. The most important one is called the touche, but there's other things here to change timbre and such. Now, this is a later Martenot. This is what you would see now. Or if you went to Paris and took Martenot lessons, first time I was in Paris and I saw, a piano studio where it said Martenot and piano lessons. I was kind of surprised. It's kind of cool. So ever since the 20s, you've been able to learn either instrument growing up. And not even to be a professional musician on either, just as part of your education for your interest. And that's still the way it is now. So Martenot players, there are quite a few very talented Martenot players. But they have controllers in the left hand. It's still a monophonic instrument. You see it has a keyboard here. I won't even talk about that. That keyboard was a late add, and it's not what interests me that much. And to me, in some sense, I'm pretty opinionated. I don't really care for the keyboard much. But anyway, we'll talk about that a little bit. But the cool thing is this ring. Okay, so on your picture, if you can't see it here, there is a ring on this person's finger, and then there's a string that goes over here to a pulley, and a string on the other side that you don't see that goes on a pulley. And so when the performer moves hands right to left, right, what it does is it pulls on that string, which goes over pulleys, and then moves a plate capacitor. The synthesis here is the same as the Theremin, the original synthesis. Some Martenot aficionados vehemently deny, no, he invented this himself. I don't know. Martenot's patent says an improvement on, and then gives Theremin's patent. So I beg to disagree. I'm not going to get into that fight. But Russians versus French, or Russians that lived in the USA versus French battles are not my thing. So that's up to you. But as far as I can tell, the synthesis method was the same as the Theremin. The big difference is you had this mechanical movement of plates rather than having your hands in the air, which meant that if you got sweaty during a performance, you still moved your hand the same way. Where if you're doing it in the air, right, that changes the capacitance. It's just the moisture of your hands, moisture of the air, any metal in the wall, all sorts of things. It changes how your tuning is going to be. So it's really nice to have this mechanical thing. So that's pretty cool. Then on the left hand, he had this button here called the touche. One of these mercury setups, which you make out of different materials nowadays, but which is very sensitive. So this is another, quote, improvement over the Theremin, that you have very fast amplitude control. You just can't move your hands fast enough to get staccato notes, to get very short notes or sharp attacks and stuff. There's some tricks about touching the antenna and various other things on Theremins, but basically Theremin has pretty slow response because it's limited by how fast you can move your hands and how precisely you can move your hands. Where a touche like that, you're only moving about 1/10 of an inch, and very fine movements let you shape sounds. So that's really cool. So here's a whole list of stuff that I thought was interesting. So these controllers in left hand, they include a switch between keyboard and ring. I got a sad face for that. To me, it just feels like a different world. Like the ring, the continuous pitch thing, just feels like it's unrelated to the keyboard. The keyboard's still monophonic, but the keyboard makes it even easier to hit the right pitch. Right? It used to be in the first version, you had the ring and then you had a painted keyboard. Kind of like the reference on the Continuum. You can move your hands and you know where you're going to land, so you can play in tune because you have a reference. But the keyboard is like Bob Moog much later, and in general, synthesizer keyboards, that's sort of what it is. On the keyboard, though, you can still use the left hand and control the amplitudes of notes, but you have locked pitch. So there's a switch between the two, and to me, it just seems like the keyboard instrument's just a separate thing. There's not a smooth transition. I've never heard a smooth transition. You can always tell which one is which. In fact, you can always tell when it's a Martenot playing or a Theremin playing, despite the fact that they have the same synthesis technique. And on the Martenot, you can tell when it's the keyboard or when it's the ring. They're just very different. But the touche is incredibly, touche just means touch. But it is really good for sensitive dynamics. That's just really incredible. The right hand does pitch, so you can shape each note if you well enough. So, about the ring, it's attached to strings over pulleys to move plate capacitors. How is this better than Theremin? Well, you can hit pitches, no matter what the circumstances are, much better. How is it not as good? It doesn't look nearly as cool. A huge part of music is the performance, right? And, when you're not even touching an instrument, that's just amazing. So there's good and bad about it, but and also just the limitations of what the Theremin does makes it quite a beautiful instrument. About the keyboard, the early version just had a false keyboard, a painted keyboard, and later they had a working keyboard plus a ring. And like if you watch Radiohead, or I don't know where else you see in this country where you see Martenots, but that's what they got. So how's a keyboard better than the ring? Well, you can play even faster. You can't play multiple notes at a time, but you can play faster. It's even easier to hit the right thing. How is it not as good? It's a keyboard. You just have, and keyboards have been around for a very, very long time, for centuries before this. It doesn't have the new features that the ring provides. There is a new instrument coming out called the Osmos, a French company that I'm working with, which does have sensitivity on the keys. Think about like something like Aftertouch, except actually super sensitive, like this touche is super sensitive. And we're working with them, and they'll have the Egan matrix in it. So in the future, if you want to hire yourself out as a sound designer, if you learn enough in here, there'll be plenty of audience for that. But anyway, they're working on that. They have a very aggressive manufacturing schedule. We'll see when it actually happens. But the same stuff as a Continuum, except it's sort of like a fretted Continuum, where it's a keyboard that's very sensitive, and continuous pressure rather than just velocity sensitivity with Aftertouch. It's a very nice thing, but not out there yet. What is out there already is this Ondes speaker. So what they did, what Martenot did, is he had this palm speaker, which was because of the shape, it has tuned strings on it. So it's kind of a hardcore, like nowadays when you design speaker enclosures, right? You can try to figure out the resonances, you can try to adjust the room, you can try to do all these things. Well, he just did this, heavy-handed thing and just had tuned strings on it. Hey, if you want a certain resonance, tune the string for it. It's kind of cool. Colors the sound nicely. It's very interesting. And it's sort of like a fixed filter. I'll talk about that a little bit later, but it's got some very cool things about it that make it sound acoustic. One of the things that makes it sound acoustic, though, that we've lost in speakers is the 3D audio field. If you go to 3D movies, right, you put on these glasses and you get one of the many cues for 3D. And people are very excited about it. But for instance, if you move your head and stuff, the right thing doesn't happen. Nobody would ever be confused about, am I watching a movie or am I really there? Very different things, right? And the same thing happens with headphones. With headphones, you can do head-related transfer functions, you can do reflection, or you can have dummy head recordings. But the fact is, it's somebody else's head that's moving around, not yours. And, the tiny little 3D cues you get aren't there. But if you have a wooden resonator like this, or a guitar body, or a violin body, or a flute, or any instrument like that, right, you really have a 3D sound field. It's very, very different than anything speakers generate. And so that's interesting. Also working with a company that makes this owned. It's a very hard sell, though, because, right, you're having people that are listening. It's like when I was a kid, they were trying to sell color TVs. We had a green and black TV. We were supposed to be black and white, but it was more like green and black. But in any case, we had this TV, and you get ads about these beautiful color TVs, and they'd show you images, but you're not looking at them on the right thing. So who knows? But anyway, so there are modern inventions that are following these. Cool. I'm going to play you an example here. This is, there are many compositions for Martenot. This is a Haken composition for owned and orchestra. One of the questions I have for you is, does it meld? Which is like, does it blend, but different? Does this instrument stick out like a sore thumb? Like when you hear like electric guitar with orchestra or something, it just feels like there's these two separate things, and they just don't meld. It's extremely difficult to do that. In this example, I'd say parts of it meld and parts of it don't. So it's kind of interesting to listen to. Sometimes it sounds like this outer space thing with an orchestra, and sometimes it sounds like it's actually part of the orchestra and complementing the orchestra rather than just being this alien thing overlaid. This is a small part of a much bigger composition. With the ring, of course, not the keyboard. All right. So quite beautiful. Now, the thing there is that the synthesis methods there were enhanced from what the original had. This was all ring playing that you were hearing there, but it was all enhanced from the original using techniques that came from Germany, from Friedrich Trautwein, and from the Trautonium. Now, this work, it's great that Martenot and others recognized this, because Trautwein was in the wrong place at the wrong time, as was Hertz, for whom the units are labeled, named, and various others, because it was just before the Nazis really took over everything. And sort of unfortunate. They used his work to show off how culturally amazing Germany is and stuff, but almost everybody, including me, assumed that most examples of this stuff were just faked by Nazis' propaganda things. It was very hard to tell what's real and what isn't in a society like that. We got the same thing now. What is actually true and what isn't depends on who you talk to on Facebook. Well, we have the same, at that time it was rampant. Same problems. So most of what Trautwein did got lost, but other people in the world did notice. Eventually there was one really famous player of his instrument, and who also improved it further, Oscar Sala, a physicist who was a good performer. But I'll talk about this a little bit. This is subtractive synthesis. So what does subtractive synthesis mean? Very different than additive, and very different than heterodyne. In subtractive synthesis, you take a harmonic-rich waveform and remove parts of it, rather than adding things in, or rather than doing heterodyning. So the most common waveform for that is a sawtooth. So one of the cool things Trautwein was able to do was he made actually an audio rate baseband, as we call it, sawtooth. He didn't use heterodyning or anything. He really had a sawtooth that was pretty stable, not really in tune by today's standards, but pretty stable. And that's cool. Then he really had figured out this idea of resonances. So a resonance of a system is where, if you looked at a frequency response of just the system, not necessarily the input to the system, but the system itself, it has peaks in it, right? So resonance peaks. Now, resonance peaks are also called formants. That's a speech name for them. Sometimes we call them spectral peak. And the overall shape of a resonance, like if you have a filter, a filter or something, the overall shape of the filter, what does it do to the spectrum? That's called the spectral envelope. There's an important phrase, spectral envelope. It comes up all the time. Most envelopes, like amplitude envelopes and frequency envelopes and stuff, are time functions. But the spectral envelope is a magnitude versus frequency function. Okay? And it's just a graph of, what is the frequency response of this filter. So Trautwein's huge innovation was to use a fixed waveform and then filter it. Okay? Now, the fixed waveform could play at different frequencies, but the filter wouldn't move frequencies all the time. The filter kept the same response. The filter's job was to act like an acoustic resonator, like the body of an instrument or something, and its job was to shape the sound, but it wasn't. It didn't shift. So it's a really important point. So I want to concentrate on that first. There's also this thing here: fixed waveform partials are always at integer multiples of fundamental. Let's talk about this whole topic below the line I drew there. Because this is very important, I put this on the handout so that. So what? Because it's easier to share that way during times of COVID. Normally, I had just drawn it on a blackboard and took a picture, but I figured that works better than trying to do that real time with Echo 360. So what happens here, if you have a sawtooth, this is a sawtooth there, and in fact, that name sort of came from the German name that Trautwein used for it. It's an exactly repeating waveform. And in fact, if you wanted to look at magnitude versus frequency, so this is linear magnitude, not dB magnitude, Makes a big difference how you do your axes. And in linear frequency, not octaves, not log frequency. Right, you have this decaying harmonics vector for a sawtooth. If the fundamental is amplitude 1, then the nth partial here, if that's partial 2, partial 3, partial 4, is amplitude 1 over n. So it sort of has that shape. And it goes on infinitely. In fact, a sawtooth has very sharp corners, and so it goes on infinitely, right? You know from your Fourier theory that any waveform that has sharp corners in it has to have infinitely high frequencies in it to represent those sharp corners. So it's just something to know because we're going to do digital stuff later, right? Sawtooth pain in the rear in digital because you don't have infinite frequencies. You can only go up to half sample rate. Anyway, that's a topic for later. So you've got this thing here. Now, any exactly repeating waveform, so where every period looks the same, can only have exact multiples of the fundamental frequency in the spectrum. So those frequency ratios of the partials that I talked about earlier can only be exact integers. Right? So any waveform, doesn't matter if it's sawtooth or not, can only have exact integer multiples of the fundamental frequency. Now that actually makes sense. Like let's say you were trying to have 1.5 times the fundamental frequency. Well, if you had a sine wave component like that, after one period, it would not, it would still be in the middle of a sine wave cycle, right? It wouldn't be at the same place it started after one period of the fundamental. Right? It has to be integer multiples. I'm not sure if that makes sense. Just think about it later. Why does it have to be integer multiples if it's going to repeat? Basically, every sine wave component has to come back to its zero crossing, its positive zero crossing at the beginning of the next period. And if it's any frequency but the integer, an integer multiple of the fundamental, that wouldn't happen. Okay, so now up here I had asked. How is this so different from the Telharmonium? Remember, the Telharmonium had drawbars, had ways to control amplitudes of the first harmonic, second harmonic, third harmonic, all the way up. All the ones it could generate, you can control its amplitudes. But if you played a low note, the third harmonic could have the same amplitude as if you played a high note. And that is not what happens in any acoustic system. It's not even an approximation of it. So let's look at this here. If you have, in the Trautonium, you had 2 peaks, 2 band passes. That's all it had, and you can do a whole lot with that, it turns out. But you had 2 spectral peaks, so this is magnitude versus frequency. And you have 2 spectral peaks in here. Look at the solid line. If that's the fundamental, right, which is common. The fundamental is often lower amplitude than other things. That's not too weird. That's what you hear, but your ear is actually hearing an aggregate of all the harmonics. So here the solid line is the fundamental, and then its first harmonic is here, second harmonic is there, third harmonic is there, right? You can see that. Now, if you feed the same thing, a sawtooth of a different, or an excitation of a different frequency in, what happens? Like say this lower one here. Well, your fundamental is even quieter, and then this guy here is a different amplitude. This third harmonic here was very quiet. Here it's much louder. You see what's happening there? You have one fixed frequency response, one spectral envelope. But depending on what pitches you feed into it, you got all these different harmonics. The harmonics are going to be different amplitudes. So it's not like drawbars. It's not like that third harmonic is always the same amplitude, no matter what pitch you play. It really depends on where on this spectral envelope does that third harmonic hit. Make sense? If it doesn't, it's an important concept. It'll come up over and over and over again in this class, but please think about it. Let's see what he has. There was a question about, is there a reason why sawtooth is used more than square waves? Yes, there actually is. Square waves are super cool, too, and they'd probably be the number 2. Or maybe noise, or maybe sine waves, I don't know. But square waves don't have all the harmonics present, right? You're skipping some of the harmonics. And so sawtooth has every harmonic present. It sounds raucous, but reasonably good by itself. And so it kind of works out. But yes, square waves are a big deal too. Absolutely. And in fact, with subtractive synthesis, you can make resonances like this, but like say you want in a square wave when you're leaving out every harmonic, you can't really imitate that with these resonances. You really do want to start with a square wave if that's what you want filtered. Because a square wave just has absolutely missing harmonics in it. And, with these resonances and stuff, they'll increase or decrease harmonics, but they won't totally get rid of one. At least not a resonant filter won't. You need a much, and so, yeah. So, yeah, that's a good question. Yeah, square waves are a big deal. And in general, I think a lot of analog synths are also based on pulse waves, where you can just adjust the duty cycle. So it's a sort of a fancier square wave. Uh-oh, we're almost out of time here. I'm going to play you an example, and then I'll have to show you this next time. But the main thing I wanted you to see here when you're listening to this example is, hey, there's a wire here over a plate. Okay? It's just a resistor divider. So one of these posts is voltage, the other one is ground. When you press down this wire, it's a resistive wire, it'll short to the plate. And if it's near the one post, it'll be a different voltage than if it's near the other post. It's a resistive wire. In modern times now, I recently came out with with a thing that uses a ribbon, a resistive ribbon. Very similar idea. Is our Continue Mini, much cheaper to build than the thing you got in the room there. In my humble opinion, not as nice to play, but I didn't say that. It's just, realistically, people just don't have the money to pay for the newer versions of what you're using in the studio there, in the lab there. But anyway, so when you press down on it, you get different pitches. So I will show you an example, and we'll continue here next time. There is a question here too about, hey, is one of the reasons that sawtooth is, is it easier to build a circuit for and stuff? All of these are a pain in the rear in digital because anything with sharp corners is hard. Sine waves are really easy, but anything with sharp corners is hard. And it's actually a big problem. We'll talk about that, but it's just when people are talking about, it seems like, hey, all I have to do is turn on and off the sine bit on this D to A, and I'll get a square wave, and no, you'll have an atrociously aliased piece of garbage, which is not a square wave. Come on, it's worked before. Oh, here it is.